Hello, welcome again on the lecture series on engineering thermodynamics. In this session, let us discuss about pure substances. At the end of this class, you should be able to explain pure substance and its behavior, and you should be able to use thermodynamic property tables and charts. So let us first discuss what exactly a pure substance is. Now, let us consider water. Water can exist in solid phase, liquid phase, and vapor phase. Maybe you call it as ice here, water here, steam here. And the chemical formula for water is H2. You take ice, its chemical formula is H2O. You take water, its chemical formula is H2O. You take steam, its chemical formula is H2O. Another thing is, let us say your water in a container, right? You take one sample here, one sample here, one sample here. Find the equation. It's H2O, it's H2O, it's H2O only. Such a substance, I call it as pure substance. A pure substance is a material with homogeneous and invariable composition. It is homogeneous, 2:1, invariable. Point to point you go, face to face you go. It's invariable composition. Pure substances can have multiple phases. As I said, solid, a liquid, correct, and vapor. Can have multiple phases. An ice water mixture is still a pure substance, but an air stream is not a pure substance. You take air. Air is a mixture of, we say, oxygen, nitrogen, and some inert gases, we say this, plus water vapor, right? And if I take samples, air samples at different places, the composition, mixture composition will be vary. So it is a mixture, it is a pure substance. So we can say a substance that has a fixed chemical composition throughout is called a pure substance. Water, nitrogen, helium, carbon dioxide. Substances which are a mixture of various elements or compounds also qualify as pure substance as long as the mixture is homogeneous. Right? If I go on take examples, the samples remain the same, that's fine. Right. Now let us look at how exactly pure substance, particularly I am talking about water. Now how exactly it behaves. So what I am going to do here is I am going to draw a temperature versus heat input diagram. Okay, here, to begin with, let me take ice here. So let me mark the state of the system. So ice, I measure its temperature. Let's say its temperature is minus 20 degrees Celsius. Correct? The heat value present is that temperature value is minus 20 degrees Celsius. So I mark the state. Next, I start supplying heat to this. So it is now in the solid phase. Solid phase. If I start heating this, its temperature increases in a linear way till the temperature becomes 0 degrees Celsius. Please know that the pressure acting on this is 1 atmosphere. Pressure acting is 1 atmosphere. I am supplying the heat. Initially it is at the solid phase. So if I start supplying heat and its temperature will increase, say it reaches to 0 degrees Celsius. Whatever amount of heat that I have supplied to bring ice from this state to this state, I'll call it as sensible heat of ice. I call it as sensible heat of ice. What is the total amount of heat supplied? Mass of the ice, specific heat of ice, and temperature rise. It is 0 degrees Celsius, minus 20 degrees Celsius. I can substitute these values. If I know specific heat of ice, mass of ice, and temperature rise, I can find out the sensible heat of ice. Okay, fine. Now it is here. This ice at 0 degrees Celsius. Now I further supply the heat. When I further supply the heat, the temperature remains same. However, here it is in the solid phase. This will become liquid phase. Here, ice is at 0 degrees Celsius, where water is at 0 degrees Celsius. This heat, I call it as latent heat of fusion. This is the mass of water. This is what you call it as latent heat of fusion. So to bring solid at ice at 0 degrees Celsius to water at 0 degrees Celsius, I have to supply heat. But if I reverse it, I want to convert water into ice, I should remove heat. So there is a phase change here, solid to liquid. This we call it as latent heat. Latent is hidden, latent heat of fusion, because it is not seen as a change in temperature. It is hidden. That's why I call it as latent. Now you have water at 0 degrees Celsius. Pressure acting is 1 atmosphere. I continue to supply heat, and gradually the temperature of water will increase. So when it reaches to something like 100 degrees Celsius, water will start boiling. Okay. This heat, whatever I have supplied, to bring water from 0 degrees Celsius to its boiling point, I call this a sensible heat of water. If I know mass of water, specific heat of water, temperature rise, I can find out the sensible heat. This boiling point, I call it as saturation point or saturation temperature. Saturation temperature. We can call it as saturation liquid state. Saturation liquid state. Liquid. Now the pressure here, so as I said, I'm maintaining constant pressure. That pressure I call it as saturation pressure. Saturation pressure. At a saturation pressure of 1 atmosphere, say saturation temperature is 100 degrees Celsius. Right. And that heat I call it as sensible heat. Sensible, I call it as whatever heat that I supply here, I call it as sensible heat of water. And normally we represent by a symbol HF. Correct. Now here latent heat of fusion are represented by HSL, solid to liquid. This is a fusion, latent heat of fusion. Now water is boiling. I continue to supply heat. Then gradually this gets converted into steam. This point it will become, all water will become water vapor, steam. This we call it as saturated vapor state. Saturated vapor. It is at temperature of 100 degrees Celsius. To convert water at boiling point into steam completely, whatever heat that we are going to supply here, this heat we call it as latent heat of vaporization. Latent heat of vaporization. So this we represented by HFG, that is liquid to gas. Okay, here solid to liquid, here liquid to gas. HFG, this represented as HF and this represented as HFG. Okay, this is latent heat. Now how much is this latent heat? How much is the latent heat of fusion? These values we can obtain from property tables, which I will explain later. Property tables. Fine. Now at this point, I continue to supply the heat. If I continue to supply the heat, this will become further, like this becomes superheated vapor. At any point here, this is what we call it as superheated steam at 150 degrees Celsius. Again, it is a linear one. This we call it as whatever heat that we supply to bring dry saturated steam to superheated steam, whatever heat that we supply, this we call it as superheat. That we call it as superheat. This we can find out Hg, gaseous state, mass, specific heat of steam, and temperature rise. And temperature rise. So this is how the steam, that is temperature versus heat input diagram, can be drawn, and different phases can be seen, right? And in this case we have assumed the pressure that is acting here is 1 atmosphere. Now if at all, if I conduct a similar kind of heating process, similar type of heating process, with say 2 atmosphere pressure. So let me draw, maybe it is something like this. sorry, it's linear, something like this, this way it will get a curve. Suppose I do the same heating process with 5 atmosphere pressure. I'll get this, get this, get this. Much higher pressure. Get this, get this, get this. You can keep observing the latent heat value keeps decreasing. Latent heat value keeps decreasing. Let us say I'll apply a pressure of almost 221 atmosphere. This simply become vapor. The latent heat may become completely zero. Correct? Now, let us look at these things. Okay, I'll join all the saturated liquid lines. I'll join all the saturated vapor lines like this. Then you can get like this. So whatever is there in this region is all in the liquid state. So L. Here partly liquid, partly vapor. So you can say L plus V. Here it's completely vapor. Here you have liquid, directly vapor. There is no L plus V state. So that's how we can understand how exactly the pure substances or water behaves under, as we input heat, also maintain different pressures, right? So this is what we call it as temperature versus heat input diagram. Now I suggest you to remember the terminology sensible heat of ice. It's given by M ice, specific heat ice, and temperature ice. Then you call it as latent heat of fusion, mass of ice into latent heat of fusion, which you can obtain from property tables. Then sensible heat of water. This is given by mass of water, specific heat of water, and temperature rise. Then latent heat of vaporization, mass into latent heat. This you can obtain from property tables. Superheat, mass, specific heat of steam, and temperature rise. Then this you remember, it is called saturated liquid point, saturated vapor point. This you call it as saturated liquid line. This you call it as saturated vapor line. This you can call it as critical point. Critical point. Okay, where when in a certain pressure, the liquid directly gets converted into vapor and the latent heat will be zero. This you can call it as critical point. Okay, so this is how the water behaves. So these definitions I have written over here. Saturation temperature and saturation pressure. So a given pressure, the temperature at which a pure substance changes phase is called a saturation temperature. Likewise, at a given temperature, the pressure at which a pure substance changes phase is called a saturation pressure. For water at a pressure of 1 atmosphere, that is 101 0.325 kilopascal. Saturation temperature is 100 degrees Celsius. Correct? At a saturation temperature of 100 degrees Celsius, saturation pressure is this. So, correct? So, these are the point. This is what exactly I am talking about. 100 degrees Celsius. And along this line, the pressure that is acting is 1 atmosphere. I have written P sat is 1 atmosphere. So, you know what is latent heat of vaporization, latent heat of fusion, correct? Saturated liquid line, saturated vapor line, and so on like this. Here I have shown a graph showing saturation pressure values and saturation temperature values. So you can see here 100 degrees Celsius, the corresponding saturation pressure can be read. At 150 degrees Celsius, corresponding saturation pressure can be read. So these are the point, right? So, correct. I also indicated already temperature versus volume also we can draw this diagram. So I have explained in the temperature versus heat input diagram. All the saturated liquid points you join them, you'll get a saturated liquid line. Similarly, saturated vapor points you join, you'll get a saturated vapor line. And this point is critical point. You can see here the critical point value is, which is the critical volume you can call it, so many meter cube per kg, and this is the critical pressure 22.09 megapascal for water, and the critical temperature is 374.14 degrees Celsius. Okay, same way with all these points we can draw it on PV diagram. Great. So you can clearly see that what is a critical point, saturated liquid line, saturated vapor line. This is how the constant temperature lines look on PV diagram. Correct? So you know you will get the constant pressure lines like this. These are constant temperature line on PV coordinates. Okay. So please understand how exactly each another property looks are drawn on different coordinate systems. So here you can see here now again pressure versus temperature diagram is drawn. So suppose you have solid, correct, then you apply like the pressure in such a way or the temperature in such a way the solid can get directly converted to vapor. So such a line you call it as sublimation line. Solid, it is not, it is in the solid phase, it is directly converting into vapor. These are the pressure and temperature values at which the solid will get converted directly into vapor. So here you see, if you follow this line, okay, then solid, then it will convert into liquid. This is what you can call it as melting. Correct? That expand on freezing. Water is the one that expands on freezing. Other substances they contract on freezing. For water, this is applicable. For those substances which contract on freezing, this line is applicable. To convert liquid into vapor, yeah, this is another line. So sublimation line, melting line, vaporization, right? So this is what you call as critical point. So from these property diagrams, we can find out what should be the pressure and temperature values to convert solid into vapor phase or solid into liquid phase or liquid into vapor phase like this. So here you see for water critical point, critical pressure, this critical point which I explained here also, or you may understand better here, correct? So at what pressure it will directly convert into vapor, that is 218 atmosphere. Temperature is 374.14 degrees Celsius, or in Kelvin 647.30. For oxygen, this is the critical pressure and critical temperature. So triple point means where solid, liquid and vapor all exist in equilibrium position. We call that as a triple point. Right? That is something 0.01 degrees Celsius for water. And oxygen, it is around minus 219 degrees Celsius. So if you see here, solid line, solid line, solid line, you draw, will definitely get is how the saturated liquid line. Similarly, you will get the saturated solid line like this. Is that okay? So here then there is something like liquid, solid and vapor existence. All if I bring in, then I will be getting that critical point. Okay. So these are some of the subscripts we follow while referring the property tables. Subscript F, properties of saturated liquid, properties of saturated vapor, Vf, specific volume of saturated liquid, Vg, specific volume of saturated vapor, Vfg, difference between Vg and Vf, Vfg, Vg minus Vf, Hfg, that is latent heat of vaporization. So these are some of the symbols that normally that we use, and while using the property tables, you should be in a position to know all this kind of thing. Remember these things. Okay, there is something like dryness fraction. So let me explain that dryness fraction. So let us consider some point here, this way. Here, if I take a sample, there will be some liquid and some vapor. This I call it as wet vapor. So I want to know how much it is dry. Right? That's why we use dryness fraction. I use the symbol X. Mass of vapor divided by total mass. That is mass of vapor divided by mass of water plus mass of vapor. Correct? So this is what the dryness fraction is. So now the question is, you want to find out dryness fraction. Let's say here Vf is the volume of liquid. Let us say Vg is the volume of gas. Vg minus Vf is Vfg. So I want to find out what is the volume at V. So V average 1 minus X of Vf plus XVG, because the dryness fraction I have to talk about. That's why here I have defined X as, correct, X as V average minus Vf divided by Vfg. Okay. So this volume, correct, total volume. So now from this I know X. From here I can calculate. So same way internal energy can be calculated. Average enthalpy can also be calculated. So if I know the drainage, you want to know the drainage fraction. If you know these values, it is possible to find the drainage fraction. Or if you know the drainage fraction, you can always find out what is the enthalpy at that point, what is the internal energy at that point, and the volume at that point. So please, this is a very useful equation. Same way, if you are trying to do with entropy values, then S average should be entropy SF plus X into entropy SFG. So knowing what is the entropy at this point and entropy at this point, we can always find out what is the entropy at this point. It's here. Okay, right. So you can just look at all this kind of definitions. Now I'll so these are the things I already mentioned, right? How do you calculate, separate, and all these things? Entropy also I mentioned to you. Now, sometimes these values have to be obtained from property tables. One of the property tables that we call it as steam table. Please look here. Saturated water pressure table is given. So here pressure values are given. Corresponding saturated temperatures are given. Suppose pressure. You see here this value 99.62 degrees Celsius. This is 1 bar. So corresponding volume. Correct. So internal energies, all these things values you can obtain. Similarly, enthalpy liquid. Then you can find out latent heat. Then you can find enthalpy vapor, saturated vapor. Similarly, you can find out entropies. So it all depends upon the notations that you see here. Depends on which author's table we are referring to. Each author uses these notations differently, correct, depending on that definitely, but it will contain only sensible heat, latent heat, and saturated vapor values. It can be enthalpy values and entropy values. Sometimes they will give you internal energy values, otherwise they may not give it at all. But definitely you will get pressure values, temperature values, also specific volume values. They may not give you the density values. Okay, this is for this, we call this as a saturated steam tables. Saturated steam tables in the market that is available as steam tables. In that you can refer to saturated steam tables. Whenever you want to refer to superheated then values, then you have to refer to superheated water vapor. So here the pressure is given and the corresponding temperatures are given. For these temperatures, you can obtain internal energy values, enthalpy values, and entropy values. So you have to get different pressures for that temperature you choose, and the property can be determined. Suppose this pressure, this temperature, you want what is the total enthalpy, so you can get this. Similarly, for 50 atmosphere, what is this value you can obtain? Maybe in between values, we have to interpolate. Either I can use linear interpolation That is one thing. I'll get an approximate value. Okay. Using many points, I can use linear interpolation and I can obtain the value. Otherwise, I can refer to some graphs. One of those graphs is what you can call it as the Moliere chart. Here, Moliere chart, that is enthalpy versus entropy chart. This is entropy, this is enthalpy. On this enthalpy, entropy, you can see these blue lines. These are all constant pressure lines. These are the pressure values given. Okay, the blue lines are constant pressure lines. These are, we call it as quality or drainage fraction lines, the red lines. Vertical lines are entropy lines. Horizontal lines are enthalpy lines. The green, these lines are, you can see this, these are temperature lines. Also, some tables you can find specific volume lines too. Correct? So, knowing any two properties, will be able to find out other property. Let us say at a pressure of something 50 bar and a temperature of 500 degrees Celsius. So you can mark the point. Correct. You can obtain the entropy. You can obtain the enthalpy. Correct. The same way you can mark a point here. You can get it, temperature. You can get the enthalpy. You can get the entropy. You can get the drainage fraction. You can also get the specific volume. So in many charts, specific volume will also be shown. So that way you can use Moliere chart and you can obtain the properties. Okay, so these are very important charts. Here I have just considered water as a pure substance and get the properties. So it can be a refrigerant that is also considered as a pure substance, which you have seen from another video. And for those pure substance also, this kind of property charts will be available and you can use those property charts. And if you know any two properties, other properties can be determined. Hope you have understood the pure substances and the behavior of pure substances, how to find the properties of pure substances at a given state. Okay, we will continue in the next session. Till then, thank you.